It turns out that the mean value theorem is an easy consequence of Rahl's theorem, stated first. Assume you have a function f from the interval ab into the reals. This function is continuous on the interval ab and differentiable on the open interval ab. Then you can find the point C in the interior, the open interval ab, such that the value of the function at b minus the value of the function at a is equal to f prime at c times b times. You rewrite this slightly differently as follows. What this seems to indicate, assume that this is the function f on the interval ab. I'll draw the line joining a fa and b fe. It will be a line where the slope is equal to fb minus fa divided by b minus a. That's the definition of the slope between these 2 points. And what the theorem tells you is that there's some point somewhere on the curve where, wrong one, a bit closer perhaps here, some point somewhere on the curve where the tangent line has exactly the same slope as the slope of the average, right? As the slope of the line joining these 2 points here. There might be more than one, but there's at least one point where that's going. You're able to compute the derivative of the function at that point C simply by computing the slope of a line joining 2 points. That's not usually going to be the way you compute the derivative, but there'll be times when, instead of working with this quotient, we'll want to work with a derivative, and vice versa as well. This theorem doesn't tell you how to find the point C. It relies on Rahl's theorem, and the existence of the point C in Rahl's theorem is not a constructive existence. It's not a constructive proof. It just tells you that it exists, so it's an existence. We'll build a new function phi on the interval ab, and it will be defined as follows. To each x, you will assign the following value. F at x minus f at a minus f at b minus f at a divided by b minus a times x minus a. Is this function well defined? Well, it is. The only way it could be ill-defined is if you're dividing by 0, but here we're going to be assuming that a is strictly smaller than b. Otherwise, one of the assumptions cannot be met. If a is equal to b, the interior, the open interval ab would be the empty set, and there's nothing in the empty set. So we are assuming, the way the theorem is stated, that a has to be strictly smaller than b. And so b is not equal to a, b minus a is not 0, we are not dividing by 0. Great, so we've built this function. What is it? It's the original function f at x. You subtract a constant, so you're going to move it up and down, and then you add to it basically a straight line. Not quite important to see what it looks like, but that's just the way you're building this function. What you do know, though, is that if you evaluate this function phi at a, you're going to get f at a minus f at a minus fb minus fa divided by b minus a times a minus a. So this is 0, this is 0, this whole thing here is 0. And in the same way, you evaluate phi at b, you're going to get f at b minus f at a minus f at b minus f at a divided by b minus a times b minus a. These cancel out. I'm left with f at b minus f at a minus f at b minus f at a, 0. So this function phi, being as it is a combination of continuous function. We know that f is continuous. You add a constant to a continuous function, it is still continuous. And then you add a linear function to that, it remains continuous because the linear function is continuous. So phi is continuous. And being a differentiable function on the interval ab, again for the same reason, differentiability is preserved by sums. The linear function here is differentiable, the constant is differentiable, the original function was differentiable, at least on the interior of the interval AB. So this new function here is also differentiable. So we have basically phi continuous on AB, differentiable on AB, phi at A is phi at B is 0. And by Gauss's theorem, Theorem 44, in these videos, there's going to be some C in the interval such that phi prime C equal to 0. But the derivative of phi at x, phi prime, is going to be simply f prime at x minus f at a. That disappears, it's a constant, so derivative is 0 minus, well, f at b minus f at a over b minus a, the constant, and then I have the derivative of x minus a, which is just 1. If I substitute x by c, I'm going to get phi prime at c, which I know is 0, being equal to f prime at c minus f at b minus f at a divided by b minus a, which means that fb minus a over b minus a is equal to f prime at c. And this, my friends, concludes the proof. We have proven the existence of a point c somewhere in the interval for which the derivative of the function at c is equal to the quotient fb minus f at a divided by b minus a. In other words, the slope of the line joining the points, the endpoints, points on the graph of the function at the endpoints. Well, there's a direct consequence to this theorem, Theorem 46, not important enough to get its own name. If f is continuous on the interval AB, differentiable on the open interval AB, then if the derivative of x is equal to 0 for every point in the interior, the function is actually a constant. Now we know the converse of that result. We know that if a function is a constant, its derivative is 0. What we're showing here is that if the derivative is 0 everywhere, the function has to be a constant. There is no other function whose derivative is 0 everywhere. Pick some x here in the semi-open, semi-closed interval AB. I know my handwriting isn't always fantastic. I have a round bracket on the left and a square bracket on the right. By the mean value theorem, you can find some point C in the interval AX, not AB, AX. If X is somewhere between A and B, greater than A, potentially equal to B, then the interval AX, closed interval AX, is an interval on which the mean value theorem applies, because the function f being continuous on the full interval AB would also be continuous on the interval AX and differentiable on the open interval AX. Just jot that down here. F is continuous on AX, is differentiable on AX, right? These are subsets. At any rate, you can find a point by the mean value theorem in the open interval AX such that f at x minus f at a divided by x minus a is equal to f prime at c. All I've really done here is I replaced the upper end, the larger endpoint of the interval AB by. But we know that the derivative of the function f at c is 0. How do we know this? By assumption, the derivative is 0 everywhere. In that case, f at x minus f at a divided by x minus a is equal to 0 for every x. I say for every x because the choice of the x was completely arbitrary. So this is true no matter what x you've picked. Multiply both sides of this equation by x minus a, which you can do because x has been selected to be strictly greater than a, so x minus a is not equal to 0, so I'm not dividing by 0 here. So put fx minus fa is 0 times x minus a, which means 0, which means that fx is equal to f at a for every x. In other words, f is a constant. It's important to realize that this is the converse of the statement about the derivative of a constant being equal to 0. Now, would we know that this is an if and only if statement? The derivative of a function is 0 if and only if that function is a constant.